Example 3 deals with proving the nature of the roots. In other words, proving that the roots are of a certain type. In 8 says, prove that the roots of this equation are real for all real values of a and b. So let's have a look at this. The equation is already in standard quadratic form. So we can write down the values of a, b, and c. So a, the x squared coefficient, is negative 2. B, the x coefficient, equals a plus b. And c, the constant, equals 4. Now, it says we must prove that the roots are real. In other words, we must prove that delta is greater than or equal to 0 for all real values of a and b. So let's work out delta. We know that it's b squared minus 4ac. Then b squared will be a plus b all squared. A, of course, is negative 2 and c is 4. I won't square out in this case, and you'll see just now why not. A minus times a minus is a plus, so we get 4 times 2 is 8, times 4 is 32. So we see that delta comes to a plus b all squared plus 32. Now, a plus b all squared is a perfect square. It will always only be either 0 or it's going to be a positive number. When it's 0, we're adding 0 to 32. So that comes to 32. So delta is equal to 32 then, which is greater than 0. And the roots will be real. When a plus b is not 0, because we're squaring it, we're going to get a positive number here. And in adding another positive number, 32, will make delta positive. And the roots will also be real. So we can then say that, therefore, delta will be greater than 0, since it's a sum of a perfect square So a perfect square, a plus b all squared, and a positive number. In other words, 32. So we know that delta will always be positive in this case, and hence the roots will be real. For any values of a and b, so for all real values of a and b. Then in b it says, show that the roots of this equation are real and rational for all values of k. First, we're going to write the equation in standard quadratic form by bringing 1 minus k to the left-hand side. So 3x squared plus k plus 2 into x. Then we're going to get plus k minus 1 equals 0. Now we can write down the values of a, b, and c. So a is 3. B, of course, is the x coefficient, which is k plus 2. And c, the constant, equals k minus 1. Now, we need to show that the roots are real and rational for all values of k. In other words, we must show that delta is firstly greater than or equal to 0, and then also a perfect square. So let's work out delta. So we know that delta is equal to b squared minus 4ac. B squared will be k plus 2 squared minus 4ac. We can simplify now. We can square out here. And we can also multiply out here. So we're going to get negative 12k plus 12. And now we can add like terms. So 4k less 12k is negative 8k, and 4 plus 12 is 16. We get a quadratic which you can factorize, and this turns out to be a perfect square. So it's k minus 4 all squared. The square root of the first term, the middle term sine, and the square root of the third term. So we see that delta is a perfect square. So delta is a perfect square. And therefore, the roots are rational or real. So the roots are real and rational for all values of k. So for all k, an element of real numbers. Then coming to the last example here, it says, show that this equation has non-real roots for all real values of p. First, we need to write the equation in standard form. So we're going to bring everything to the left-hand side. It's not yet in standard form because we have two terms in x squared. So we can rewrite this as one term in x squared by taking out x squared as a common factor. Now the equation is in standard quadratic form because we have one term in x squared, one term in x, and a constant. Now we need to show that this equation has non-real roots. So we need to show that delta is less than 0 for all real values of p. So let's first write down the values of a, b, and c. So a, the x squared coefficient, is p squared plus 1. b, the x coefficient, is negative p. And c, the constant, is 2. We need to show that delta is less than 0. So let's work out delta. It's going to be b squared less 4ac. We can simplify, so it's p squared minus 8p squared minus 8. We can add like terms. So p squared minus 8p squared is negative 7p squared. So delta turns out to be negative 7p squared minus 8. And we need to show that this is always negative for every real value of p, or any real value of p. The way we're going to do this is by taking out a negative. So we get negative into 7p squared plus 8. Let's look more closely at what's inside the brackets here. 7p squared is always going to be either 0 when p is 0 or positive when p is non-zero. If 7p squared is 0, we'll get 0 plus 8, which is positive. If p is non-zero, then 7p squared will still be a positive number, and we get a positive number plus another positive number, which is always positive. So what's inside the brackets will always be positive. Then we have a negative times a positive, which will give a negative. And that means that delta is negative. Now, to write this down, we're first going to say that 7p squared plus 8 is always going to be greater than 0 for all p an element of real numbers. Therefore, delta is going to be negative. And the reason for this is that a negative times a positive is a negative. So that's what we can state. since a negative times a positive is a negative. So a negative times a positive is a negative, and hence delta is less than 0. And now we can state, therefore, the roots are non-real. For all p an element of real numbers. So let's look at your answers to this question. In A, we have to prove that the roots of this equation are real for all real values of A, B, and P. Now, the equation is already in standard form, so we can write down the values of A, B, and C. So A then, the x squared coefficient, is equal to 1. B, the x coefficient, is negative into A plus B. So we must include the sign here. And then C, the constant, is going to be AB minus P squared. So everything that doesn't have an x in it. Now, we need to prove that the roots are real for all real values of A, B, and P. That means that we have to prove that delta is greater than or equal to 0. So let's find delta. So B squared minus 4AC we can square out here. A negative squared is a positive, and in squaring out A plus B, we get A squared plus 2AB plus B squared. Here we can multiply out. Now we can add like terms. So 2AB minus 4AB is minus 2AB. And what we notice now is that here we have a perfect square. So we can factorize it. So the square root of the first term, the middle term sign, and the square root of the third term, all squared. So we end up with the sum of two perfect squares. A minus B squared is a perfect square, and 4P squared is a perfect square. So we know that the sum of two perfect squares will either be 0 or positive. So we can say, therefore, delta is greater than or equal to 0. And the reason we give is, since a sum of two perfect squares. And now we can conclude that the roots are real. And we needed to show that it's true for all values of A, B, and P. So we can add this. The roots are therefore real for all real values of A, B, and P. Let's look at B. It says prove that this equation has rational roots for all rational values of K. This equation is already in standard form, so we can start by writing down the values of A, B, and C. So A is 2, B equals K plus 2, and C equals K. Now, in order to show that the roots are rational, we need to show that delta is a perfect square. So let's work out delta. It's going to be b squared minus 4 times a times c. We're going to square out here, so k squared plus 4k plus 4 minus 8k. We can add like terms, so 4k less 8k is negative 4k. And we get a trinomial or quadratic here, which we can factorize, and it's actually a perfect square. So square root of the first term, middle term sine, square root of the third term, all squared. So now we simply write that delta is a perfect square, and hence the roots will be real and rational. So hence the roots are real and rational for all values of k, and in particular for rational values of k. Then in C it says, show that this equation has non-real roots for all real values of m. So first we need to write the equation in standard quadratic form, and we're going to bring everything to the left-hand side. We want only one term in x squared, so we're going to take out a common factor from these two terms. So then m squared plus 1 multiplied by x squared. Now the equation is in standard form, so we can write down a, b, and c. A is going to be m squared plus 1. B is negative m. And c, of course, is 1. Now, we need to show that the roots are non-real. So we need to show that delta is less than 0. So let's work out delta. So b squared will be negative m squared. A is m squared plus 1. And c, of course, is 1. So we have b squared minus 4ac. Now we can simplify, we can square out here. And we can multiply the negative 4 into the brackets. We can add like terms. So m squared less 4m squared is negative 3m squared. So delta turns out to be negative 3m squared minus 4. And we need to show that this is always going to be negative for all values of m. So we can take out the negative here, and we get 3m squared plus 4. Now 3m squared, because the m squared is, or the m is squared, 3m squared will either be 0 or it will be positive. If it's 0, then we're going to get plus 4 inside the brackets. And if it's positive, if 3m squared is positive, then we're going to get a positive number plus a positive number here. So what's inside the brackets will always be positive. So we'll have a negative times a positive, which is a negative. Then to write that down, so we say that 3m squared plus 4 is always going to be greater than 0. So for all m, an element of real numbers. And therefore, delta is going to be negative, since a negative times a positive equals a negative. Since delta is negative, we can say that the roots are non-real. So thus, the roots are non-real. Then indeed says, show that the roots of this equation will be real and unequal for all real values of m. First, we're going to write this equation in standard form, and we can easily do so by bringing everything to the left-hand side. So there's no need to multiply out here. This is now in standard form, and we can write down the values of a, b, and c. A is 1. B, the x coefficient, is negative into m plus 2. And c, the constant, equals m. Now, we need to show that the roots are real and unequal. That means that we have to show that delta is strictly greater than 0. So let's work out delta. So it's b squared minus 4 times a times c. We can square out here. A negative squared, of course, is a positive, and m plus 2 all squared is m squared plus 4m plus 4. We can see here that 4m cancels with negative 4m, and we're left with m squared plus 4. So we have the sum of a perfect square and a positive number. Now, a perfect square is always either positive or 0. Let's say it's 0. Let's say m squared is 0. Then delta will equal positive 4. If m is a non-zero number, when we square it, we're going to get a positive number, and a positive plus a positive is a positive. So delta will always be positive, irrespective of the value of m. So we're going to start by saying that m squared plus 4 is greater than 0 for all m an element of real numbers. And we can also add the reason for this. It's a sum of a perfect square and a positive number. So hence delta, which is equal to m squared plus 4, will be greater than 0 for all m an element of real numbers. And hence the roots will be real and unequal.